Hello, and here we are. Thank you again for joining Containers from the Couch today. I'm your host, Justin Garrison, and with me today is Jimmy Ray. I always switched it, man. Forget the sides. How's it going, Jimmy?
I'm doing well, thanks.
And we have a special guest with us today talking about Litmus Chaos. Karthik, go ahead and say hello and what you're doing.
Hey everyone, thanks Justin for having me on this session of Continuous from Couch. Great to be here. Very happy to discuss chaos engineering with you all. So I am a principal engineer at Harness and one of the maintainers of the Litmus open source project. So yeah, very happy to be here. Hoping to have a great interactive session today.
I am very excited to see how we can break stuff. It's always a fun thing to do. So, but first, let's just real quick give people that maybe not familiar. What is just an overview of chaos engineering in general? Like, why do they want it? Usually, we want to reduce entropy in chaos. So, what is the point of having chaos engineering in our architecture and in our systems?
Yeah, it's a great question to start off. There's a lot of friction around the word chaos engineering. A lot of people call it by other names. Reliability engineering is probably another way that's more palatable to hear. And you could define it in very simplistic terms as a vaccine that helps us build immunity from outages. I'm just trying to use that analogy because of the times that we're in right now, something that is generally going around a lot. So this is basically controlled injection of failures into your deployment environment to ensure that you understand the system behavior better, try to train the incident teams, to try to ensure that you find out causes of outages much before they actually happen in production, and then go ahead and fix it. The fix could be something with a change in the application business logic, maybe some deployment practice, something that you might have tuned in your infrastructure. So it's basically helping to do controlled failures. It's always associated with some kind of hypothesis or expectation around how the system should behave as part of a chaos experiment. That's what chaos engineering is all about. It's about experimentation. So as part of an experiment, there's a hypothesis, expectation of how the system should behave, and it's about whether that is proved or no. No is better because you get to learn more about the system and that way fix it. So that's a very quick introduction to what is chaos engineering.
So this is, I guess, primarily trying to, inoculate yourself against the unexpected, right, disruptions that could possibly occur. I mean, when I look at it, I think about making sure that my object references can withstand null pointers and that type of thing. So from a programming perspective, that's usually unexpected and runtime errors type thing.
Absolutely. Yeah, so the production environment is very dynamic. It's basically a live representation of the Murphy's law. Anything that can go wrong will go wrong. So there can be a lot of things that might not have been accounted for when the code was built or when the deployment was done. So some of those things do occur in production, and it's always good to be prepared beforehand. Try and dig those problems out as early as possible. The original principles of chaos that Netflix and other folks, initial pioneers, put together says that you need to do chaos in production. That's really the ideal case. I would say the nirvana of a very mature chaos practice, but a lot of the times, and especially we are seeing that now, chaos engineering is done in pre-production environments, not just by the SREs, but a lot of other persona. And we try to minimize chances of the system going down at the outset at AVD personas level. That's the effort that they make using chaos engineering.
And I like how you called out that another word for it is reliability engineering. Like reliability is the goal. We just, how do we make things more reliable? And Jimmy was kind of alluding also to like test-driven development, right? Like if I don't want to avoid a null pointer, I write a test for it. And in my code, that's fine. I can control that environment. I write a test. I'm not doing experiments against that test, right? A unit test is just like, I sent this thing, I expected this thing. in a way, like I'm saying my hypothesis and my outcome of that test. And if it fails, then I'm not going to deploy it, right? Because I just want to avoid that in production. With systems, they're much more complex. They're not just this one function. They're not just this one application. It's multiple systems tying together, talking together. And with all of those things that can fail, that's where chaos engineering really plays a part, where you're writing tests at the system level, not at an individual function or service level.
That's true. You made a great point about the comparison with functional tests or unit tests. A lot of the times, these tests focus on the how of the product, whereas chaos engineering comes in at the what level. That is, you have a set of SLOs that's defined for the product, and you're often trying to look at what's happening to those SLOs when a particular fault is injected. So it is really at the end user level or the system level that we're trying to measure. Having said that, most of the tools or frameworks that enable you to do chaos engineering can also be used to do something that's probably more granular, and it's trying to do some kind of functional validation as well. But that's about how it is being employed, how you're sort of bending the tool. But in a sense, the practice of chaos is always about the end user or system level goals, trying to validate the resilience at that level.
And so how does, or I guess, where does Litmus KS come into this, right? You have this open source tool, which actually let me actually send a link to chat so people can check it out too. But you have this open source tool that implements some of these practices of chaos engineering. And what's the goal of having an open source tool here? Why do we want to enable people to do this?
Yeah, so I'll probably give you a little bit of history, try not to bore you with it, but at some point, we were trying to write up a resilience test suite. You can call it some kind of an extended E2E suite for another open source project called OpenEBS. This was about 4 years ago, four odd years ago. And one of the things that we were trying to do was get the same experience in doing operations around OpenEBS that was being used for, let's say the day-to-day functions. Let me elaborate. So OpenEBS is a Kubernetes native storage solution. And by the term Kubernetes native, we mean that everything right from its packaging to deployment to the way it's managed, everything is done in terms of YAMLs, resources, and there are some controllers that reconcile these resources. That's pretty much the case with most things on Kubernetes today. And when we wanted to include resilience testing and chaos testing into this context, we wanted it to follow the same paradigm that was already being used for other things, Kubernetes. So we didn't really have, at that point, Chaos Monkey and a few other solutions that were there. Of course, they were good chaos tools, but they were not optimized for Kubernetes, not in terms of attacking Kubernetes targets, Kubernetes deployments or pods on one hand, and on the other hand, the way in which the tool was utilized was not really Kubernetes native. So that's when we went ahead and wrote up Litmus Chaos. And over a period of time, it acquired a roadmap of its own, became more generic, and we sort of modeled it into a generic chaos engineering framework. And again, we sort of completed that circle by having to target not just Kubernetes components, but also components that reside outside of the Kubernetes scope. Infrastructure pieces, for example, nodes, cloud instances or VMs or disks, things like that, but all executed from within Kubernetes control plane, the fault, as well as the expectation around the fault injection, that is your hypothesis, is all defined inside of a Kubernetes custom resource. So that is really the differentiator that we were trying to bring about with Litmus. And there are features that got added into the project as we went along based on community feedback. For example, we added more probe types. Probes are essentially ways to validate certain expectations around your fault injection. You could be hitting an HTTP endpoint to check for some health. You could be doing some PromQL queries to measure how your metrics are changing. You could be doing some Kubernetes commands. You could be running something that's completely custom as part of your validation. And then we also increased the fault types. We started off by writing some simple pod failures, and then that went on to add network and resource failures. And then there were some application-specific failures that got added. And that's sort of been the journey of the project. And we eventually added a control plane to go ahead and manage chaos across your fleet of clusters. So you have different target environments where you want to do chaos. Would like to manage that all from a single control plane. And you would also need the ability to consume the chaos artifacts from a single source, that is the Git, as a single source of truth. You would like to collaborate with your team members on your chaos experiments. So these are some features that got incrementally added to the project to sort of bring it where it is at this point. And this is when we submitted it for CNCF as an incubating project. So we entered incubation stage earlier this year. So that's been a story about Litmus. To summarize it, so Litmus was written up as a need for cloud-native chaos engineering. So the chaos engineering principles is always been our spiritual sort of guiding principles, but we added a few other postulates to it. The fact that the experiments should lend themselves for automation. They should be declarative in nature. There should be a standard structure to the experiment. There should be some open APIs using which different people can come in and write their own chaos business logic, but have the way of defining the experiment similar, so that the operationalization of this is easy. The way they invoke it, the way they consume results, the way they monitor it, all this is made standard, whereas the actual business logic can be anything. So some of this was added as extra principles, cloud native chaos principles, to what was already there. And Litmus is an implementation of these principles.
Cool. I'm interested to see it. Like, do we want to dive in to see what it can do and kind of a demo on how to use it?
Sure. So what we'll do is dive right into the demo. There's a very simple chaos use case that I can show up. And once we've seen that demo, we can come back and take a look at a couple of architecture diagrams and flowcharts so that it sort of reinforces some of the concepts that we just discussed. And we can also connect the dots because we've already seen the demo. So with that, let me go ahead and just show what the demo is about. So I've taken a simple application, microservices application called SockShop from Vworks. It's a popular demo application which gives you a e-commerce shopping experience where you can buy socks. There are different services that make up this SockShop application. As you can see, there's a front end, there's a website where you can go and shop for the socks. And then there are different services that help with ordering and payments. And there's a catalog that shows you different kinds of products, socks related products, etc. Some of these are stateful microservices. They have some DB, SQL, and NoSQL DBs associated with it. So this is the sample application that we're going to use for chaos. So as a user, we're trying to simulate this SRE persona. And what we're trying to do is we are looking at certain constraints. Always, we're looking at certain properties of SockShop. Availability is one attribute, and the performance is another one. Availability is basically the expectation around availability is that it's always going to be active. The website is always going to be alive for me to go and do the shopping. It has 100% uptime. And performance is a minimum set of transaction per second or latency that I expect out of the website, out of the shopping website. Right. So these are some of the things that, let's say, I'm already monitoring for. Let's say I have a Grafana dashboard where I'm looking at it. And then we'd like to test some assumptions about what's going to happen when there is a fault injected on a simple fault that's injected on some of the microservices. In fact, the intent is, let's say there's something that happened inside the cluster, one of the pods got killed. In Kubernetes, there are great chances for your pod to sort of just get rescheduled or killed. There might be many reasons. It might have got evicted. the node might have gone down. So many reasons why a pod can go down. And let's say in our case, we're actually going to inject a failure on one of the pods, the catalog pod. The catalog microservice is the one that's powering the SOX catalog. So let's say we are, as an SRE, I'm going to go ahead and run a sample scenario where we go and kill a catalog pod. And we see what happens to my availability and performance. And these constraints around availability and performance are going to be tested along with the fault injection as part of the overall experiment run. And we're going to get a verdict based on how this probing goes. For example, if my constraints around availability and performance were met, if that's my steady state hypothesis. If that was met, then I have a pass verdict for the experiment. In case they were not, then we will get a failure. The verdict in Litmus is something that's an opinionated expression of the experiment result. It's something that SREs can choose to use or ignore because they might derive their own inferences by looking at their own observability dashboards around what happens. For them, it might be just the fault injection that's useful. Whereas if you're running it as part of an automated run, maybe in a pipeline, you could use the verdict to go ahead and fail the CI or the pipeline jobs and sort of get an idea of how things run.
And how does Litmus actually inject that fault? Right, we want to make a pod go away or have problems. Is this a sidecar proxy? Yeah. Is this a wrapper script for init? Like, how is it actually doing that injection?
It's a great question. So the injection itself depends upon the nature of the fault. In case of something like pod delete, which is what we're going to do right now, it's a simple Kube API call that we're going to make. So in case of Litmus, one of the outcomes of running it in the cloud native way is that the experiment business logic is containerized and runs as a pod. So you have a custom resource that gets created on the cluster, and there are some operators that are watching this custom resource, and they launch some child resources. These are transient pods that carry out the business logic of the fault, as well as the steady state validation. So in this case, we're going to create a pod that actually runs that basically makes a Kube API server call to kill the catalog pod. So this is for things like pod delete or node drains, or you're putting in eviction taint or things like that. In case you're trying to do a network or a resource test, let's say I'm doing a packet drop, I'm trying to inject some latency between microservices. In those cases, we leverage some container runtime APIs. We might be trying to figure out the container ID, and then we might be trying to enter the network namespace of the container and run some firewall rule or run some TC commands or run some stress processes by entering the process namespace. So some of those need us to run a container that sort of co-resides with this application container that we're trying to target on the same node, because we will be trying to use the runtime APIs on the same node. So the nature of the fault injection determines how we run the experiment. Sometimes it's just a pod that can come up anywhere and run a Kube API call. Or sometimes it needs us to run a container that's sort of co-residing with the application container, and we basically do the fault there.
Cool. And one question from the audience was QuantiTV about wondering if the cart should be connected to order. We're not actually talking about the architecture of the app itself. I did put a link to it. It's an open source project, SOX Shop. It's used in a lot of demos, and they have a really cool just environment to be able to deploy this. Kubernetes, Docker Compose locally, lots of different ways to run it, and then also ways to like just have an example sort of load test on it. So if you've never run or tried SOX Shop before, it's a really fun, just sort of like microservices demo for a lot of different things that can integrate, and then you can figure out how it breaks.
So, but with with some of these faults, right? You mentioned stress the system. When I think about stressing a Kubernetes cluster, there's points that I want to look at, like, how can I stress the API server, or how can I under the cover stress, API server talking to etcd or etcd itself, or perhaps maybe I'm stressing the kubelet on the node. So is that something that's within the scope of capabilities of Litmus?
Yes, it's a great point. So the stress that I was alluding to in the previous conversation was about how you eat up resources within the node or within the pod, and this is the CPU, memory, or disk resources. Having said that, it's perfectly possible to do things like stress the API server, make multiple calls, or stress the probably the node in terms of how many pods that it can run, and maybe you're testing your auto scaler functionality through that. Or we can basically go ahead and do some action that stresses the kubelet. Those are possible. Litmus offers a set of off-the-shelf experiments, ready-made chaos experiments, as you could call them. But it also has the concept of BYOC, bring your own chaos. That is, we talked about the open API or the Litmus experiment structure. So there is a scaffolding tool that you could use to bootstrap your experiment, which basically creates some skeletal version of the experiment, which does things like a pre-chaos check, the fault, the post-chaos check, and pushes all the events, writes all the logs, etc. And then you could go fill in the right functions. That is the business logic that you want to do for doing the actual faults. And then you basically wrap it in a custom resource, which then gets orchestrated with Litmus control plane. So it's possible to write up, what I'm trying to say through this is it's possible to write up newer experiments fairly quickly in Litmus and expand the test library that you have.
So do we have an experiment that we can run and check it out and see some outcomes?
Sure. So we talked about this SockSharp demo. I'll probably show you that in action. So I've just set up some prior runs. I was doing a dry run of the demo setup. So the chaos control plane, let me explain, or let me take a few minutes to explain how the chaos platform, the Litmus chaos platform, is set up. So I have this running on an EKS cluster, which is, and I've got some services exposed via load balancer. In the Litmus namespace, and I've created all this by just applying a Kubernetes manifest. You could do this via an Helm install as well. I've used the version 2.9.0, which is the latest release of open source Litmus. And when you install this in your environment, you will see about 4 deployments running. In fact, 3 deployments and a stateful set. The auth server, a front end, and a chaos server, along with MongoDB, which maintains the, is basically your chaos database. And this is what comprises the chaos control plane, or the CPC as we call it. And what you're seeing here is the dashboard, the front end that we will log into and create our chaos workflows and execute it against our target environment. So let me log in as admin. I will talk about the rest of the deployments that you saw in the namespace in just a minute. So I've just logged in as admin using the default credentials that you have in a secret when you install it. And you will be logged in into your project. So each user in the chaos center, that's the dashboard name, is assigned their own project space. As you can think of it as a chaos workspace. And the admin would typically go ahead and create more users. They can go to the settings and add more users and provide some username and password to them. And they could map some target chaos environments for these users. And when the users log in with those credentials, they will be entering their own respective project or workspace. And they have the option of then inviting other team members into their project in different roles. You could be inviting a new member as a viewer, or as an editor, or as an owner of the project. So typically, most of the initial evaluation happens as an admin. So that's what I'm going to show in this demo as well. So the Litmus workflows that you see, you could think of these as chaos scenarios or the chaos test case. So this test case or scenario may make use of one fault in this, as we are going to do in our current demo. We're just going to use the pod delete fault, the pod kill fault. But you might want to simulate a complex case where, let's say, you want to go and stress a node. You want to heat it to its capacity in terms of resources, and then you want to go ahead and evict a pod in another node. Because these kind of situations do happen in production. Your failures there are a result of things getting built up over a period of time rather than isolated occurrences. So let's say you want to simulate a complex condition. So you could be doing some faults in parallel. And you would be picking the faults when you construct a workflow from here. You would actually be picking faults from the chaos hub. So this is like a open catalog of readily available experiments within Litmus. They're all categorized based on the environment that they act against. So most of these that you see in generic category, they are the standard Kubernetes faults. You can see pod delete, or see network faults, or pod level resource faults, etc. And this list is basically going to continue with some other type of faults. So you could actually go ahead and create a custom workflow by picking the faults from this chaos hub and then execute it against the target environment that hosts your business applications, or which is where your infrastructure component that you want to target resides. So you can see there is something called agent here, and this is also something that you can see listed in the agents screen. So this is the execution plane, or the CEP as we call it, the chaos execution plane. So this is where the action actually happens. So this is where the chaos actually gets played out. So this could be the same cluster where you have the control plane services running, in which case we just call it the self agent. So to aid simpler evaluation and to just get people started quickly, whenever the admin logs in for the first time and the admin project is created, we also try to install the execution plane components on the same cluster, which is when this agent auto-magically registers or connects itself into the control plane. And that's when you would see some of these other non-highlighted deployments coming up. So there are a couple of custom controllers. You can see there's a chaos operator. So this is the one that watches the chaos engine custom resource. That's one of the custom resources which actually triggers the experiment run. There's something called as an event tracker. So this helps with monitoring application changes on your cluster and then triggering some chaos workflows. There's something called a workflow controller. So basically executes tasks as part of a larger workflow. Let's say you had one or more faults picked as part of your workflow in some order, sequence, or in serial fashion, or in some parallel fashion. Or sometimes you might have tasks that are not exactly chaos tasks, but there might be some preparatory tasks, or there might be some cleanup tasks. There might be some load job that you want to run as part of it, some synthetic load that you want to run during your fault injection. So each of those are available as tasks within a workflow. The workflow controller executes those tasks. So this is actually an Argo workflow controller under the hood. And one of those tasks happens to be running the chaos, which is when the chaos operator comes into picture. And there's a chaos exporter, which is basically trying to collect some Prometheus metrics around your experiment occurrence, experiment run. And one of the most important pieces is the subscriber. So this is the one that acts as a bridge or relay between your control plane and your execution plane. This is the one that applies your workflow manifest. This is the one that relays the events back to the control plane and how the experiment is progressing, etc. So these components, the exporter, the operator, and the subscriber, the workflow controller, these get created when the execution plane is installed. So like I said, for aiding simple evaluation, this is automatically set up upon admin project creation. But the usual flow for the users, let's say the day one or the day two operations associated with chaos would be for the users to set up the execution plane inside their own clusters, external clusters that they connect here, because they might have their applications running elsewhere. In this case, I've connected an external cluster, which I've named EKS cluster 02, which houses another sock shop instance, just for illustration purpose. And this connectivity is aided by a tool called Litmus CTL. It's a simple, when you say connect an external agent, you will have some instructions here. You can download the Litmus CTL binary and you can run some commands. You can do a set account and create agent. This is an interactive command that takes some inputs on how would you like to name your execution plane, what is the control plane URL that you actually want to connect to, etc. And also the service account that you want to use on your execution plane to carry out these faults, a host of such information. So we'll talk about how the interaction happens between the control plane and execution plane. What is the flow of the experiment? What are the individual stages of a given experiment? And some capabilities of Litmus, etc., in subsequent, in the discussion that will follow. For now, I'll go ahead and show the fault in progress. I will select the self agent. That's the local cluster, which is where I'm running the WeaveSox microservice. I am monitoring WeaveSox SockShop application on Grafana. Just trying to track what is the queries per second and latency average values. And I will have some expectation around the availability of this website, as well as some of these performance attributes, because we said as part of the demo, we will look at these two constraints, availability and performance. So I'm going to select the self agent, coming back to the screen.
Just also calling out, like, that's like prerequisite number one. Like, if you want to do chaos engineering, you need to measure the things. Like, you can't improve the things you don't measure. You can't run experiments and not collect data. So make sure that you have good alerting and measurements in place before you start jumping down the chaos engineering rabbit hole. Because I've seen a lot of folks that chaos engineering is cool, like they want to go down that route, and then it's just like, hey, actually, do you have a good dashboard? Like, do you have alerts, and do you know what's going to happen in this case if you start breaking things intentionally? And so just shout out to anyone else that wants to do it. Make sure that you have something in place that's monitoring and measuring this stuff.
Absolutely. I think observability is very important for chaos engineering. I think without that, we would not be able to make much sense out of the fault injection process. So going to the next screen, this is basically a set of options, different ways in which you can run workflows. While you're using it for the first time, you might be using the third option, that is, you're creating the workflow by picking the faults from the Chaos Hub. Like I said, I'll show that in a bit, but before we sort of see what options you can select and how you can tune it, etc. In the interest of time, I just wanted to create a workflow by cloning an existing one. So we already did a few workflow runs for doing the catalog pod kill. So I'm just going to go ahead and select the workflow that I've already ran, and then just clone it and run it again. So this is an equivalent of a local template. And when I say local template, that means that there can be a template that's not local. That is that's the predefined chaos workflow. That is, once you've created a workflow, if you feel that it makes sense, it represents your use case correctly, and you want to use it repeatedly, have a golden copy of it, you can actually push it to a Git repository and then consume it from there. So whatever you see here on the Chaos Hub, so this is actually rendered from a canonical source, which is actually a Git repo. So each of these faults is a meta, that whatever you're seeing here, whatever you see rendered here, all that is basically a YAML file that is sitting in a specific directory structure in a Git repo. And you could be putting use cases or scenarios or workflows there as well. For example, there's a simple workflow here called potato head chaos workflow. You could be creating your own workflows and push it to Git and then just create out a library of workflows like that, whatever makes sense for your application. And then
can you show us an example of some of the YAML for a workflow and a test? It was someone in the comments asked as well, just to see like, what does that look like? How much YAML am I going to write? It's cool that you have basically like an app store for chaos. That's pretty awesome. But also curious because everyone's going to want to tweak those or do their own thing for their specific needs.
Sure. So I'll just show you the YAML that gets generated at the end of this workflow wizard. So this is the template that we selected. And let's see. So this is the experiment that we already have. You can see a few things here.
Can you make that bigger?
The pod delete. Yeah, let me go ahead and make this bigger.
Oh,
okay, I hope this is better.
It's a little better.
Yeah, so we have a couple of things that you can see here. We've picked the pod delete fault, and we are doing this against an application that bears the label name equals to catalog. That's the key value that we are selecting, and it is within the sock shop namespace. And we have got a couple of probes here. We are basically trying to do the availability and performance check. I'll show you how that looks like. I go to next. So this slider is basically a way to provide some weightage or points to the faults that you're using within a workflow. So sometimes when you're constructing a workflow, you would like to do a set of faults, but you have an expectation or an idea of how much toleration or tolerance you have to that fault based on the application maturity at the point when you're running these workflows. Sometimes you believe that this particular application or microservice should be really tolerant to pod delete chaos or pod kill faults, but maybe not so much for a stress or a network fault. So you could give really low points to that one and give more points to the pod delete one, because ultimately you will end up with a resilience score associated with a workflow run. That is basically a metric that connects your application with the chaos scenario or the workflow and tells you how resilient the application has been to that workflow. And that metric is created or is useful because you can use it as a means to compare runs. You could be running this workflow against different environments. We could be running it on dev, QA, pre-prod, prod, or you could be doing the same workflow against different builds of your application. Then you can compare and see how that resilience score has changed over time. You might get some trend. So that's what this is useful for. So I just have one fault, so I gave all the points to it. We have the option of scheduling it once or scheduling it repeatedly in case you want some kind of repeated run based on cron. So I'm going to do a single schedule, and then you will end up with some summary like this. And here's where you can view the YAML. You can see this is a workflow kind. And the useful things to note in this workflow are, there are a couple of steps. The first one is installation of the experiment template from the hub. That's a prerequisite. And then you have a step to do the actual experiments, the pod delete experiment, right? And for each of these steps, there are some YAML files associated with it or like custom resources associated with it. They are embedded within this artifacts input and then just applied onto the cluster. The custom resource that's more useful, the one that is actually tuned or lends itself to tuning on the workflow wizard is this one. It's the chaos engine. And you can see that this is actually the bridge where you say, this is the fault that we want to do. That's the pod delete that we want to do against a particular application microservice instance. This could be a pod fault or it could be a node fault as well. Here is where you connect the node fault against, let's say, a node name or a node label. Or in case of cloud faults, it's probably where you map a fault against instance ID or a cloud instance tag, things like that. And this is also where we do the steady state validation checks. So we have two checks, the availability and performance, like we discussed earlier. So this is how the availability check looks like. It uses something called as an HTTP probe. And we are trying to hit this catalog endpoint. And we're trying to make this get call. And we're trying to look for a 200 response. And we're going to do this in continuous manner. We have a polling interval of 1 second, so it's a pretty aggressive probe. It's going to keep looking for the availability of the sock shop catalog. And in case it fails for some reason, then we've given ourselves some retries and the interval between retries. So this is, let's say, you can call it as the toleration that we have for failure. Maybe you can accept this level of degradation, but probably not beyond that, right?
Where does that probe URL come from? I noticed you're using the external ELB endpoint and not an internal Kubernetes service. Is there a reason to do it that way, or was that auto-detected from the service itself?
So we've set this probe as part of construction of the workflow. I just gave this URL because I thought it would be simpler to show it, relate it easier. So this is basically the catalog. So we just hit the catalog API, but you could be using an internal Kubernetes service IP as well. So in cases of infrastructure faults, let's say you're targeting some EC2 instance or targeting an EBS disk for detachment or some such case, you might want to go ahead and check for some health indicator which might not be technically a GitHub, a Kubernetes service URL. It could be something else. So you can put that up here as well, but you could be using either of them. And the next one is a performance check. So here we are running a Prometheus Probe. I have a Prometheus instance here, which is monitoring, which is getting some shock metrics as well as the chaos metrics. The chaos metrics, we've also used it as an annotation on Grafana to see when the chaos is active. So we'll talk about that. So this is basically a PromQL query that you can see that we are running. We're trying to get some successful queries for catalog. We're basically taking all the 200 status code queries, and we're trying to average it out and check if we are always maintaining a minimum of 75 QPS. So this is there or thereabouts. We're trying to be conservative in giving a lesser number. And we also have a mode which is different from the previous probe. So you can see the mode here says edge. What this means is I probably am okay to take some amount of performance dip because we are doing a fault, but I would expect the performance to get back to this minimum UPS in the period that we've defined here. So within, let's say, around 10 to 15 seconds, I would expect things to come back to 75. You can think of this loosely as your MTTR, or the mean time to recovery. There's self-heal built in, which you expect generally in Kubernetes environments. You would get back to optimal values or expected values within a given period of time. We're going to do this fault before, we're going to do this probe before the fault injection, just to check we are good. We are not already in degraded performance state. Then we're going to check for the same level of performance immediately after we finish the fault injection, or we've lifted the fault. So that's the mode. Other mode that support. There are a few other modes that are supported. We could be doing a purely start of test or end of test kind of probes as well, depending upon the need. Sometimes you can use these probes to enforce some kind of gating conditions. You might not want to execute an experiment. This is especially true for automated runs of the experiment. Sometimes they're not interested in running the experiment if you detect a certain condition on the cluster. So you could make an SOT probe out of that, the one that executes before the fault injection. So you could see that, okay, this is not healthy for me to run the experiment. And then you could abort the experiment based on the probe results as well.
And this is the safeguards you need for running this in production, right? I mean, that's like, we want you to run this against your production workloads. This is intended to be safe enough to do, but you need to set those levels appropriately so you don't accidentally take down a production environment.
Right. That was really the reason for some of these probe modes. So these are all guardrails that you can use. So we could go ahead and finish the wizard here, and then that will take us to the workflow table. So you can see that this is a visual representation of the steps that we saw in the YAML file. There's going to be an install experiment stage where we're going to pull the template and install it on the cluster as a prerequisite, followed by the application of the chaos engine CR, which is when the fault actually starts occurring. So let's go ahead and take a look at what happens in the sock shop namespace. So in this demonstration, we are basically trying to set ourselves up for failure. We've not done a really resilient deployment of sock shop. There's just one replica of the catalog pod running. And this has a readiness probe with an init delay seconds of, I think, around 60 seconds. So when we're actually going to do a pod kill, we're going to have a window where there's no real web catalog available. You can see this is now getting terminated. This is the pod delete experiment that's running. The fault is running here. And if you look at the catalog at this point, you can actually see that it will not load successfully. So when we started out, going back to our initial demo sort of overview that we did before coming to this, we said as an SRE, we're going to test our assumption on what happens when one replica of the catalog pod, a random pod failure of the catalog microservice happens. When that happened, we expected things will all be running, but unfortunately, did not hold true. So we have the catalog that's not come up. So in this case, when the SRE would come back and check, they would root cause it to an inefficient deployment practice of having deployed it with less replica count. So maybe the remediation is to scale the replicas and then see if that fixes the problem.
All right.
So that brings up a question. Incident response. And what do we do when these things, happen, these unexpected disruptions, so to speak? So is there a best practices guide or patterns for when you do these types of experiments and you see these outcomes? Are there a set of best practices to fix, or prevent or lessen the outcome of these disruptions?
It's a great question. We've been able to draw up some playbooks, so to say, based on our experience trying to sort of do some dog fooding of Litmus for our own SaaS platforms, or having learned from the community on what all remediation actions that they have taken. So in case of pod delete faults, let's say we talked about increasing the replica count. There could be a host of other actions that people might do. For example, there might be checks against observability sometimes. If we are receiving the alerts at the right time for some kind of unavailability, it's important that the mean time to detect is very less in our platform, the MTTD, and we have an opportunity to go and at least manually take some remediation action, or if there is some kind of self-heal that we can automate and build in. Sometimes for pod delete experiments, it's also about how quickly we are able to reschedule, or how quickly we are able to instantiate the autoscaler. In case of multi-replica deployments, killing one pod, which takes a long time to come up, will put additional stress on the other pods. So there might be resource spikes there, which we would need to detect, and whether your autoscaler is coming into picture and trying to mitigate that scenario. So those are checks that people would do. So each experiment, like you said, has its own set of things that they can check and then they can act on to remediate. So we've gathered some of that information. We've not put it out as a best practice guide, but that's something that we're definitely looking at doing, adding to each experiment's documentation on Litmus.
Well, and some of that matters. I mean, like that's the whole point of doing these science experiments, right? You have a hypothesis, the output should be this. You probably have some hypothesis of like why that may or may not be the case. But the goal of an experiment is to learn, and you may not know, like, I don't know why this didn't work, but that's, you now have some data to start with, and you say, okay, I can measure this over time. I love that this lets you do those sort of cron sort of checks over time to have baselines and just like, oh, what changed? Switch back to the Grafana tab, because I love that slider there too, of just like, here's where it ran, right? Like I could see exactly when Litmus Chaos was running. And okay, well, the problem probably came from some experiment that was running at that time. And now I can go dig into that and say, okay, what did it do? And let me work backwards from there and say, okay, I can run these manually. These are just cube control commands essentially that I can run. I have some workflow with something that I can dissect and say, okay, what did it do? Why did it do it? What stage did it fail at? Because it looks like, you know, the Litmus UI and API is giving me all that information of what's failing or what didn't go as expected. So that's a really cool way just to get started and say, okay, now I need to go backwards from where we started at and see how do we make it so that my hypothesis is true at the end, or I just change my understanding of the system.
Exactly. Sometimes it could be just that we change the understanding of the system. Maybe there's a timeout setting that we need to change. To basically get a successful result, and maybe it's a practical thing to do depending upon the kind of resources being utilized within the cluster. So like you said, this annotation here is helping us find out, so this is when the chaos happened. This is especially useful for some automated runs where when some application behavior you saw, you might want to know whether the source of that or the cause of that is actually a chaos experiment, or there was a natural issue that's happened, which you probably want to learn about and reproduce as an experiment later. So this is going to help with that. And coming to the chaos dashboard, you can see that there was a failure as we thought there would be. And there are some logs here that actually tell us that some of these probe checks actually failed. There was a performance check which passed in the pre-chaos stage. This is the edge mode probe that we did for performance. And then we actually had this failing in our post-chaos stage. The availability check failed, as well as our the performance check failed as well. We got lesser values than 75, did not recover in time. So that went ahead and caused a failure of the experiment.
And
so when we go ahead,
we're right about at time. So was there, I didn't know if there's one more thing we want to wrap up for the workflow and show off, or?
Yeah, so you saw how this experiment behaves. Now, when we go ahead and fix this experiment, when we are sort of comfortable with the remediation that we made, we could go ahead and rerun it. So this instance that you see here was run after the replica count was increased, and then it succeeded. And then you could go to the analytics section and then basically do some workflow comparisons to see what's the resilient trend, whether it's increasing or decreasing, things like that. I probably just like to conclude by giving a very high-level picture of the topology, or what really happens, what is the flow of control, because this gives an idea of how things can be set up and what are the prerequisites, what are the access considerations that you might have. So typically the control plane consists, like I said, of the dashboard, the auth servers, and the database, etc. And then you have the execution plane, which is where all these components run, your exporter, workflow controller, agent, etc. As a user, we just went ahead, logged in using our credentials. We accessed it via load balancer. You could be setting up ingress, or you might be opening some ports on your firewall. And then we went ahead and created a workflow. You could be doing that manually, or you could be doing that via an API call. And then that workflow is applied by the subscriber. The workflow task contains a chaos engine setup, chaos engine application. So when that is created, the chaos controller goes ahead and runs your experiment pods that go ahead and target your applications, does the right fault, and then you get a chaos result. The chaos result is converted as a metric, and you could also use that to go ahead and provide an experiment verdict. And there's also something called an asset discovery that you would do. The subscriber also tells you when you freshly create a workflow, what all microservices are there, what namespaces are there, what labels are present, etc. And you also retrieve logs like we just saw a few minutes back on what happened during the course of the experiment. So this is really the control flow that's available in Litmus today. And with that, I'll probably stop. I can take any questions around this.
Cool. Let me drop the screen share there. Because yeah, we're right about time. This has been awesome just to see how much Litmus Chaos can do. Like when I remember when this was announced, I was just like, okay, cool. I understand some of it. But a lot's been added. Workflows and being able to see the history over time and scheduling, and the analytics looks like it'd be really way more valuable than just giving me SSH keys into production and saying like, go for it. We want to make sure this is measured and experimented properly with hypothesis and at a scale, not just to like infrastructure size, but team size, right? When I have 1 or 2 people, it's easy to kind of run these things and just make sure we're in sync. But if I have 10, 20 people managing infrastructure, if I have 50 or 100 people deploying applications, like a lot of those like homegrown, oh yeah, just hit the load balancer, right? Like I can curl it, I can run Apache Bench or something. That stuff doesn't scale very well to like larger team sizes. So that makes a lot of sense why having this sort of platform framework in place is just more useful for the larger scales.
Yeah.
Thank you so much, Jimmy and Karthik, for joining. This is, again, it's really cool. If anyone wants to reach out online, head over. We have the Litmus Chaos GitHub in the chats, so you can find it on GitHub, open issues, give it a shot. It's free to use, open source. Go ahead and give it a shot. I think it's a really cool solution to try. So thanks everyone for coming, and we will see you again soon.
Thank you.